Hello there, welcome back to another video. Today we're going to be using integration to find the volumes of irregular shapes. We're going to be finding volumes of shapes like water drops, and I'm going to show you that that's actually really easy. And I'm also going to show you a couple more examples where we find the volume of irregular shapes through the disk method, washer method, and shell method. And it's actually way easier than you think. So let's get straight into it. So we'll start off with the first question, and that's the volume around the curve y is equal to x squared from 0 to 1. So it's this area, and what happens is we rotate this around the x-axis to make a circle. Now let me show you a simulation so you can really understand what I'm talking about. Right here is the completed area for our little graph, and this is what we're gonna try to calculate. So let's get straight into it. First of all, our first step will always be to find the integral of the function we're trying to find the volume of. So in this case, we're trying to find the volume of x squared. So we got to find the integral of x squared from 0 to 1. So we always have to remember our boundaries. So from 0 to 1. So x squared is pretty simple. We just use inverse power rule. So that's x to the power of 2 plus 1 divided by 2 plus 1. And then we close the bracket and we put 0 to 1. Lovely jubbly. And then we can simplify this, so it'll be x cubed divided by 3 from 0 to 1. Now, in order to evaluate this 0 and 1, what we need to do is we need to set up an equation. So we take the upper function, we plug it into our equation, so it's 1 over 3. And then we subtract this from our lower boundary, which is 0, so 0 over 3. And that'll give us 1 over 3. So that's the area under our graph right now. Okay, lovely. Now the next step is to find the area of a circle. Yeah, you'd be surprised, but the area of a circle is actually really important here. So what is the formula for the area of a circle? Well, that's pi r squared. And now this is the fun part. So what I'm going to do is I'm going to pull up the simulation again. And now I'm going to rotate this so that you can't really see the function and it really turns into a line. And what we're going to do is we're going to rotate this function across the x-axis as a circle. And if you notice, the height of the function actually becomes our radius, right? So we take the integral. So the integral gives us the area. That actually becomes our radius. And what we do is we take the integral and rotate it all the way around the x-axis, and that's why we use pi r squared. So in this case, what happens is we say pi, and then what we do is we multiply this by the integral of x squared dx squared, because this here becomes our radius, right? If we look at it from the angle I just showed you, that becomes our radius. So in this case, it'll be pi times 1 over 3 squared. Right? And now all we got to do is just evaluate this. So it's pi times 1 over 9, which leaves us with pi over 9. And that right there is the final answer. So this entire cone-like shape has a volume of pi over 9 units cubed. And that's how you solve a volume problem. So if it ever tells you to rotate a function about the x-axis or the y-axis, this is the process you would solve it by. You use the formula pi times the integral of f of x dx squared. And that'll give you the volume encompassed by rotating any function about the x-axis. Okay, now let's move on to our next question. This one's slightly trickier, but it follows the same process. We need to find the volume of y is equal to x cubed from 0 to 2 about the y-axis. So in this case, what's happening is this function is rotating this way across the y-axis. In the last question, we had it like this. But that's not the case anymore. And this is slightly more complicated, but in order to fix this, all we have to do is take the inverse function. And I'll explain what this means in a second, but let's find the inverse function first. So we get y is equal to x cubed, and we flip the x's and y's. So we get x is equal to y cubed, which means y is equal to the cube root of x. Okay, great, that wasn't too bad. Right? Let me pull up Desmos and let me show you what exactly this means. So this is our original graph, y is equal to x cubed. And as you notice, we have to flip this around the y-axis, which means it's not very easy to do if we try to do it this way. Instead, by finding the inverse function, what we've done is we've flipped the x-axis and the y-axis, which means now, with this new function, y is equal to cube root of x, instead of rotating about the y-axis, we can just rotate this about the x-axis, and it'll give us the exact same answer. Because what we've just done is we flipped the axes, right? And this will make our process a lot easier. So let's draw out this function. We get this, something like this. And this is y is equal to cube root of x. And in this case, one thing we do need to keep in mind is that our x values and y values will switch, right? So in this case, in my original function, my x value was 2. And my y value then, my corresponding y value, is 2 cubed, which will be 8, right? So what we need to do now is we need to take this function again, and we need to swap these values. So now we get 8 as my x value, and 2 as my y value, right? And now I got to find this area here of my function, right? So let's do that right now. Let's find the integral of this function. So we get the integral from 0 to 8 of the cube root of x dx. Okay, now one more thing I want to do is I want to write this in algebraic form. So 0 to 8 of x to the power of 1 over 3 dx. Now what we can do is we can just use power rule here, right? So we get x to the 1/3 plus 1 divided by 1/3 plus 1, which is the same as x to the power of 1/3 plus 3 over 3 divided by 1/3 plus 3 over 3. And this right here will give us x to the power of 4 over 3 divided by 4 over 3. And then what we can actually do is we can flip our fraction and we can put that in front. So we get x to the power of 4 over 3 times 3 over 4. And then all we got to do is put our little bracket here, and we got to put our boundary, so that's 0 and 8, and boom. Now what we can do is we can plug in these values. So we plug in the top value first. So you get 3 over 4, 8 to the power of 4 over 3, minus, and then 3 over 4 times 0 to the power of 4 over 3. Now this, anything multiplied by 0 is 0, which means we're only left with this expression here. In this case, if you do 8 to the power of 4, it's more complicated than finding the cube root of 8, right? So in this case, what we can do is we can say 3 over 4, and then the cube root of 8 is just 2, so we get 2 to the power of 4. And 2 to the power of 4 is 16, so we get 3 over 4 times 16, and then 16 and 4 can cancel out, so 16 is 4 times 4, which leaves us with 4, which means the area under this curve is 12 units squared, right? And now all we got to do is set this as our radius in our equation for the area of a circle. So you got pi r squared, and our r will become 12, so it'll be pi times 12 squared. And what we've just done now is we've rotated it, which means now we get an area of 144 pi. And that right there is the volume of this shape rotated about the x-axis. Here's a simulation just to show you what that exactly looks like, and that's the volume right there. So I hope that wasn't too difficult. Let's go on to our final problem. In this problem, we're trying to find the volume between two curves. So it says volume between y is equal to x squared and y is equal to the square root of x when rotated about the x-axis. So when it's rotated about the x-axis, we don't have to find any inverse function. Great. But okay, it tells us to find the volume between these two curves. So we need to identify first we need to identify where they intersect, right? To set our boundaries. So they intersect once at 0, and then they intersect once at this point, right? So in order to find this point here, we need to set these equations equal to each other. So you get x cubed is equal to square root of x, and then we can square both sides. So you get x to the power of 3 times 2 is equal to x, right? And then we can do x to the power of 6 minus x is equal to 0 to find the root. And then we can factor out x. So we get x to the power of 5 minus 1 is equal to 0, right? Now, we have already found this root where x is equal to 0, so we got to look at this root now. So x to the power of 5 is equal to 1. So we say, using zero product rule, we say x to the power of 5 minus 1 is equal to 0, which means x to the power of 5 is equal to 0. And then we take the fifth root of everything, but don't worry, it's not too complicated. We take the fifth root of everything, which gives us, we cancel the 5 power at the root, which just gives us x is equal to 1. So this point right here is 1. The x value is 1. And then the y value, we can just plug it into this function. So y is equal to the square root of 1, which is also 1. Right? So we find this point of 1, 1. Now the way we find this area underneath this curve is actually quite interesting. So what we have to do first is we have to take the area of our upper curve. Like that. And then we want to find the area of our lower curve. So something like that. And basically what happens is, I'm using yellow to show that these two cancel out. So in this case, all of this cancels out because you're going to subtract the two areas, right? Which leaves us with this nice area right here. And that's what we're going to rotate about the x-axis. So that's what we're going to bring like this. Okay, now how do we set up an equation for this? I want to start off by saying that instead of using your typical integration, the integral of one function minus the integral of the other, we want to plug this into our equation pi r squared straight away. In this case, we can rewrite r as area as well. So because it's just the integral, right? So we can say pi times the area squared. Now in this case, we have two areas and both of those are squared, right? So what we can actually say is pi times the area of the top function squared minus the area of the bottom function squared. So something like that. This is the integral we're trying to set up here. So let's try and set this up. So you get pi times the area of the top function, which is, we need to use integration. So that's the integral of square root of x dx. So that's the integral of the square root of x dx, and then we want to and that's from the point 0 to 1, and we want to square this minus, and then we take the area of the bottom function, which is x cubed. So that's the integral from 0 to 1 of x cubed dx, and we want to square that too. So right there, that's our equation. Now, in order to be as organized as possible, I would suggest solving each of these integrals separately and then squaring the answer you get. Since this does look like a long problem, most of the time you will be able to use calculator for this problem, but this is quite simple in that the calculations in this question are not too complicated. So I'm going to solve this by hand, but you can skip past this part if you are not interested in solving this problem. So let's get into it. Let's solve the leftmost equation first, and I'll put this in green. So you get the integral of 0 to 1 of square root of x dx. And then we can rewrite this as an algebraic equation. So we get x to the power of 1/2 dx. And then we use our inverse power rule. So you get x to the power of 3/2 divided by 3/2 from 0 to 1. And then we can rewrite this as x to the power of 3/2 times 2/3, because we take the reciprocal from 0 to 1. And then we got to plug in our values. So we get 2/3 times 1 to the power of 2/3 minus 2/3 times 0 to the power of 2/3. Now, this cancels out because it's 0, which leaves us with 2/3 times 1 to the power of 2/3. 1 to the power of anything is just 1. So that means that the area of this function will be 2/3. And then we can square this. We need to square this, which gives us 4 over 9. Okay, I hope that wasn't too difficult. And then let's try the next part now. I'll put this one in yellow. Now let's try the next mini question here. So we get the integral, I'll separate this. So we get the integral of x cubed from 1 to 0 dx. And we want to square that at the end. But then let's solve this. So, and we want to square that. Remember to square this at the end. So we get x to the power of 3 plus 1 divided by 3 plus 1 from 0 to 1. And that leaves us with x to the power of 4 divided by 4 from 0 to 1. And now let's plug in our values. So we get 1 to the power of 4 divided by 4 minus 0 to the power of 4 divided by 4. So this cancels out, which leaves us with just 1 over 4. And then we remember to square this because this is a volume question. And that leaves us with 1 over 16. Now we can combine these values and put them into our equation. Pi times 4 over 9 minus 1 over 16. Now, in order to calculate this, we need to find the common factor of these fractions, which means we need to do the crisscross, applesauce, butterfly, whatever method you call it. So it's pi times and then 16 times 4 minus 9 divided by 144. So that will give us pi times 48, pi times 64 minus 9 divided by 144. And then we can subtract 9 from 64, so we get pi times 55 divided by 144. And I don't think we need to simplify that any further, so we can just say 55 pi divided by 144. And that right there is the volume of this little function rotated about the x-axis. Most of the time, these questions are usually given on calculator sections, which means you don't need to do all these calculations here. But it is nice to practice. So, okay, now there's a bonus question. You can choose to do this or not, but this is a little fun one, and we're trying to find the volume of a raindrop. You can just enjoy the process. I'll be moving a little bit faster than usual, but yeah, this should be fun. So straight away, we get our function y is equal to 1 square root of 1 minus x. So straight away, we have our function y is equal to x times the square root of 1 minus x. Now this is going to be a little bit difficult to integrate, but it should be fine. And what we're going to do is we're going to rotate this about the x-axis, and we're going to get this lovely raindrop shape. So let's try this. So we use a formula, pi times the integral of x times square root of 1 minus x dx, and we square that, and the integral is from 0 to 1. So let's first solve this integral inside here, and I'll use blue for this. So straight away we get 0, 1, x times square root of 1 minus x dx. Now the thing is, we can't open up this bracket because there's two terms inside here and only one term on the x. So this is going to be a little bit tricky to open up the bracket. So what we're going to use is u substitution here. We're going to set u as 1 minus x, so we can get this whole term as just one variable, right? And that'll make sense in a second. U is equal to 1 minus x, which means du over dx is equal to -1, which means du is equal to negative dx, or we can actually flip that around. Negative du is equal to positive dx, right? So that was pretty easy to substitute. And then what we got to do is we got to substitute this x as well, right? But we have an equation here, u is equal to 1 minus x. So actually what we can just do is we can isolate x here. So we get u is equal to 1 minus x, and then we can subtract 1 from both sides, and then we can add x to both sides, so we get u plus x is equal to 1, and then we can subtract u from this, so we get x is equal to 1 minus u. Okay, now we can do all our substitutions, right? So substituting everything, we get integral from 0 to 1 of 1 minus u so that's our x, that's this, times the square root of u times negative du, right? And then we can bring the negative outside. Oh, actually, one more thing we could do is we could simplify this function, this fraction here. What we could do is simplify this bracket here. So instead of 1 minus u, we can change the signs of this. So what we can do is we can say it's u minus 1, right? And then we can get rid of this negative sign. Now that makes everything a little bit easier. And then we get square root of u du. Great. Now, it seems like we haven't gotten anywhere, but we have. What we can now do is we can distribute this square root term across both these values. So we get integral from 1 to 0 of u times u to the 1/2 minus u to the 1/2, right? All I've done is convert this into algebraic form, du. Before we continue with the next few steps, we also want to write down our upper and lower boundaries. Since we do u substitution, our boundaries will change. So let's write upper and lower. So since our base equation is u is equal to 1 minus x, we can say u upper is equal to 1 minus the upper boundary, which is 1, which is 0. And then the u lower is equal to 1 minus 0, which is equal to 1. So what we've basically just done is we've flipped these boundaries here. Okay? So it'll be from 1 to 0 of u to the power u times u to the power of 1/2 minus u to the power of 1/2 du. Now, since we flip these boundaries, another rule we can sort of follow is we can just make this a negative, and then we can flip the boundaries again. So that's another rule of integration. So we've just done that. We flipped the boundaries, but we've made it negative. And now we can transfer this negative sign into the problem. So we get 1, 0, and then we can make this a plus, and we can make this a negative, and we can get rid of this. So you get u to the 1/2 minus u to the 3/2 du. Minus u times u to the 1/2 du. Now, this is u to the power of 1 times u to the power of 1/2. So what we can actually do is we can add the powers. So you get u to the 1/2 minus u to the 1 plus 1/2. Now we can write 1/2. Now you can write 1 as 2/2. So that will make it u to the power of 3/2, right? So it'll be 1 to 0 to 1, u to the 1/2 minus u to the 3/2 du. Now we can integrate these individual terms. So u to the 1/2, we add 1, so this is our inverse power rule, plus 1. And since this is the same as 2/2, and this is also 2/2, we can say this is u to the power of 3/2. And then we can take the reciprocal, of this fraction here. So that's 3/2. And then we can flip it upside down, so we get 2/3 u to the 3/2. Great, and then let's do this one now. So u to the 3/2 plus 1 divided by u to the 3/2 plus 1. We can change the 1 to 2/2. This one also to 2/2. So we get u to the 5/2. And then since it's divided by, we can take the reciprocal again, so it's 2/5, u to the 5/2. Then we can combine these, and be sure to put the negative sign. There's a negative sign there. So we can combine these and we get 2/3 u to the 3/2 minus 2/5 u to the 5/2 from 0 to 1. Okay, now we plug in the upper bound, so we get 2/3 minus 2/5. We put that in a bracket, minus, and then we plug in the lower bound. If you plug in 0 into here, this cancels to 0, and this also cancels to 0. So we can just leave it as 0. So our final answer then would be 2/3 minus 2/5. And then we can multiply everything by, then we can cross multiply. So you get 10. So we do a little bit of crisscross applesauce, multiply this. So you get 2 times 5 minus 2 times 3 divided by 15. So you get 10 minus 6/15, which will give us 4/15. That right there is the area under our graph, right? All we got to do now is we apply this into our pi r squared formula. So it's pi times 4/15 squared. And that'll give us pi times 16 over 225. And we can write that as 16 pi over 225 units cubed. So what we've just done here is we found the volume of a raindrop. And we can apply this now to any raindrop. So all we got to do is take the height of the raindrop basically and plug it in here. So if a raindrop is 1 centimeter high, all we got to say is it's 16 pi over 225 centimeters cubed in volume. And this is completely useless. I don't think it's used in many scenarios, but it is cool. And I hope you find it cool too. And yeah, integration can help you. One of the main uses of integration is finding volumes of shapes. And it can be used in all different kinds of scenarios. Here are a couple more situations where you can use volume through integration to calculate the volume of really irregular shapes. But yeah, that's about it for this video. I hope this was fun and also helpful in explaining volume. And I'll see you in the next video where we go through volume with different kinds of cross sections. And we'll go through that next time. So I'll see you then.
Bye-bye.